in many problems, be they physics, economics, biology, or many other fields of study, you can reduce interesting problems down to finding the area under some curve, as in the area between some curve and the x-axis. So if you want to generalize a bit, often you want your goal to be to find the area of some region. And that region is defined by specifying a function and then finding the area in that region. Now, in some cases, it's pretty easy to find because, for instance, if your function is a line, some kind of linear function, so f of x is equal to cx plus d, then the plot becomes a bit like this. So here's my a and my b. There's my function at some line. Y equals cx plus d. That's the equation of a line. And I want to find the area of this region. The area of this region is an area of a trapezoid. And if you remember your geometry, you probably remember that the area of a trapezoid is 1/2 the width times the sum of the bases. So the first base would be something like CA plus D, and the second base is CB plus D. Fair enough. If your function's a line, you could find that area, no problem. If your function's not a line, well, maybe it's a circle. Oops. Let's say your function is a semicircle. So like 1 minus x squared is an equation of a semicircle. It's a semicircle of radius 1. Well, what's the area of that? Well, I think everyone knows the area of a circle is pi r squared. So this is pi 1 squared, but there's only half of it. Great. Well, it stands to reason then that if you can chop up your region into pieces that you know the area of, you can find out the area under the curve. This idea is known for a long time. The ancient Greeks knew about it for sure, and they used it to find areas of lots of interesting regions. So take your function and chop it up. This can be kind of coarse, a bit like splitting a piece of wood. Okay, this chopping idea works pretty well if you know what the shape is of that function. But if you come back to our original problem where we have an arbitrary function, so here's our axes, and we've got an arbitrary function that does something. I don't exactly know what it is, but I'm after this area here between a and b, and this is some y is equal to f of x, some arbitrary function. You want the area of this? Well, that's a little bit hard. But now if you're looking at this, maybe what you need to do, instead of chopping it up with an axe, we need to cut it up into little slices. Now, cutting straight lines doesn't require an axe, it requires a power tool. So the way the integral works is, since we have a power tool, we can make all of these pieces the same size. That makes finding their area much easier, so you can find the area of your whole function much easier. Now, normally we like our functions to be above the axis, at least when we're thinking about drawing those functions. So we've got this function, we've cut it up into little strips. These little vertical strips we can find the area, at least if we ignore the little top pieces here, that last little bit before I made the cut. that'll be a little bit of error. And of course, well, there's a lot of other error as well that can crop into your approximation if you're not careful. But the idea is if you make these strips thinner and thinner and thinner, well, of course everything will turn into sawdust. But if you keep track of that, because we can find the area of each of these little rectangles, you can find the area under this whole curve here. Coming back to our function here, we've sliced it up with our chainsaw. It's now in little strips. You want to know the area of each of these strips, but you know the tops are curved. So if we flatten them out, now there'll be areas of rectangles. And those I think we can find the area of, because I think we know what the area of a rectangle. Area of rectangle is base times height. So we're going to add up the area for the first rectangle, area of the second, and the third, and the fourth, and the fifth, and the sixth, so that however many there happen to be. Okay, well let's say that we wanted n rectangles. Well, how wide is the base of each rectangle? Well, it's the width of the interval that I'm going to be trying to add up here. It's b minus a over n. And the heights vary. Okay, so I know the width of each base, the heights vary, and what I'm going to have to do is I'm going to have to add them up. Okay, well what's the first height? Well, now I've got some choices I need to make. If I take the point that's on the left at each time for each rectangle, in fact I haven't done that here, let me do that. If I take the point that's on the left each time, I won't exactly follow the function. Sometimes I'll be a little over it, and sometimes I'll be a little under it, and sometimes I'll do a pretty good job. So if I take the left endpoint at each time, I need the x coordinate. Well, this first one is a, and this one is a plus b minus a over h, over n rather, and this one is a plus b minus a over n, but there's two of them, times 2, and so on. I don't have enough room to write all the others here, but I can say the first height is f of a. The second is f of a plus b minus a over n, and so on. So for the typical, the nth rectangle, for rectangle number n, what is that? Well, let's actually move that over here. For rectangle number n, it'll be f of a plus b minus a over n, but there's a bunch of copies of them. How many are there? Well, let's see. For n being 1, the first one, it's times 0, so I need an n minus 1 here. So you could think here of this quantity in the parentheses. This is the x coordinate of left endpoint for the rectangle. And now all I need to do is add up all of these guys. Adding up all of these guys on its own sounds like a pain, but we have sigma notation at our disposal. So the area estimate is, well, I'm going to sigma from n equals 1 to capital N. The base is the same for everyone, b minus a over capital N. And the heights vary. They're just this formula above.
And great, that's an area estimate with n rectangles, and this is the left endpoint formula. I could just as well come up with a different estimate. It won't be numerically the same, but it'll look pretty similar. Starts out the same. It's got the same width, but if I were to take the right endpoints, my first right endpoint starts out already with this extra base shifted over, and so this is for the right endpoints. Okay, now if I now take lots and lots of rectangles, the hope here is that actually I'll come up with, well, the area under this curve. All of these little errors that I've drawn in red or green, or haven't shown either, all that extra sawdust there will go away. And so the Riemann sum is the limit as capital N goes to infinity of either one of these formulas. So let me just grab the right endpoint formula. The Riemann sum is that. And we usually write the Riemann sum using integral notation. Integral from a to b of f of x dx. Now, the thing to realize is this looks very different, but the pieces actually fit together. See, the dx is this guy here. And the f of something or other, it's f of some points, that's this. And the a's and b's show you the endpoints. They don't really show up in the sum formula. But now the important fact, the important Riemann sum theorem, says that if f is piecewise continuous, then left endpoint formula is equal to the right endpoint formula. Now, that's not true as I've written it, but it is true as n goes to infinity. So if I take the limits as I've written there, then it doesn't matter if you use the left or right endpoints. If you're only using finitely many points, you got to watch out. You'll have some